Hey, what's up everyone? Today we're going to be doing the equilibrium section of the 2024 USNCO local exam. So this is from questions 31 through 36. Let's start with question 31. The Ka of formic acid is that. What is the equilibrium constant for the reaction below? If you notice, this reaction is really a sum of two reactions. The first reaction is HCO to H, formic acid, dissociating to form HCO2 minus and H plus. And the second reaction is the reverse autoionization of water. So it's OH plus H plus reacting to form H2O, water. Now, as I said, the sum of these reactions is going to be our overall reaction. And you can verify this. You see that the H pluses cancel out. And if you add these up, it's exactly what you want, this overall final reaction. We know that the top reaction has an equilibrium constant of Ka. And the bottom reaction is the reverse autoionization of water, so that is going to be 1 over Kw. So the overall equilibrium constant for this is K, and we know that that's going to be the product of these two constituent reactions, so Ka times 1 over Kw. So this is going to be 1.8 times 10 to the minus 4 over 10 to the minus 14th. And this works out to 1.8 times 10 to the 10th, which is answer choice C. Let's move on to question 32. Solid calcium carbonate is in equilibrium as described below. If CO2 gas is added to the system in a rigid container, what changes will take place? So we're given two options. One says additional calcium carbonate will precipitate, and two says that the pH will increase. So when we add carbon dioxide gas to the system, we're adding products, and the system is going to be like, well, I have too many products. How do I get rid of products? Well, it's going to increase the rate of the reverse reaction. This is Le Chatelier's principle. I'm not French, so if I said that wrong, I apologize. But essentially, you have too many products, and the system is going to increase the rate of the reverse reaction to use up those products. So additional calcium carbonate will not precipitate. In fact, less of it will precipitate, more of it will dissolve into its ions. So 1 is wrong. Let's look at 2. The pH will increase. Well, if you increase the rate of the reverse reaction, you're going to have more of your HCO3 minus, your bicarbonate ion, and this is slightly acidic. So your pH will actually decrease. It's also possible that the pH doesn't really do anything because bicarbonate can act as both an acid and a base. It's weakly acidic, but it can act as both. So it's possible that the pH doesn't change at all. However, it's very unlikely that pH will increase. There's no reason to. Therefore, our answer is answer choice D. Let's move on to question 33. Calcium carbonate occurs in two common crystalline forms, calcite and aragonite. I think that's how you say it. Which of these is most thermodynamically stable? Well, in order to find out which one is more stable, let's look at which one has a lower Ksp. Because if it has a lower Ksp, then it's less likely to dissolve. So it's more stable in its solid form, whichever one has the lowest Ksp. And we realize that calcite has a lower Ksp than aragonite. So calcite is more thermodynamically stable. Your answer is answer choice A. Let's move on to question 34. What is the pH of a 0.043 molar solution of hydroiodic acid? Now, hydroiodic acid is a strong acid, meaning it's going to dissociate completely into the H plus and the I minus ion. So if you start out with 0.043 molar solution of HI, your concentration of H by the end is going to be the exact same, 0.043. One, because the coefficients are the same, they have the same ratio, and two, because hydroiodic is a strong acid, therefore it dissociates completely. Now the pH formula is that pH is equal to the negative log of the concentration of H plus. So that's going to be the negative log of 0.043 molar. And if you calculate it, your pH is about 1.37, which is answer choice B. Let's move on to question 35. At 1200 Kelvin, the equilibrium constant for this reaction is that a mixture of 0.79 bar N2 and 0.21 bar O2 is prepared at 300 Kelvin and heated to 1200 Kelvin while maintaining a constant total pressure of 1 bar. What is the equilibrium partial pressure of NO at 1200 Kelvin? it might be helpful to write down the Kp formula, which tells you that Kp is equal to the partial pressure of, in this case, NO squared over the partial pressure of N2 times the partial pressure of O2. This is from your Kp formula. And we're told that at 1200 Kelvin, which is what we care about, this value is 2.9 times 10 to the minus 7th. We can do another thing with this equation that will be helpful. We can define what the partial pressure is. We know that the partial pressure of something like NO is going to be the mole fraction of NO times the total pressure. So if you notice, this equation can boil down to the mole fraction of NO squared times the total pressure squared over the mole fraction of N2 times the mole fraction of O2 times P squared. 1P is coming from this partial pressure term and 1P is coming from that term. So they overall create P squared. And you notice that you can cancel these out. So your Kp value is going to be the same as the mole fraction of NO squared over the partial pressure mole fraction of N2 times the mole fraction of O2. This is pretty helpful because we know that your pressure is proportional to the number of moles. So we can essentially say that our initial mole fraction of NO is going to be 0. We can say that the initial mole fraction of N2 is 0.79 and the initial mole fraction of O2 is going to be 0.21. This is coming from the fact that we're given our initial partial pressures. You can treat this as a partial pressure because you know your overall pressure is 1 bar. So your partial pressure is going to be 0.79 divided by 1. So that's fine. Now we can talk about these mole fractions at the final state. So X O2 final, the final mole fraction of O2 final is going to be 0.21 minus whatever is consumed, X. Let's define it as X. And so that means that your final mole fraction of N2 final is going to be 0.79 minus also X because these are in a 1-to-1 ratio. And finally, your mole fraction, your final mole fraction of NO is going to be 2X because while these are in a 1-to-1 ratio, NO has a coefficient of 2, so twice as much is formed as is individually consumed of the N2 and O2. This is pretty helpful because now you can plug this into your original Kp formula. So if I erase this and I start filling these in, so N2 we know final is going to be 2x squared. This term we found is 0.79 minus x, and this term is 0.21 minus x. And again, we know that all of this is equal to the Kp that we're given, which is 2.9 times 10 to the minus 7th. With this formula, you can now solve for x. So we know that 2x squared, so 4x squared, is going to equal 2.9 times 10 to the minus 7th times 0.79 minus x times 0.21 minus x. And if you notice, this is a quadratic equation. It's not a very nice one, but this is very solvable, especially because you're given a calculator on the test. It might be easier for you to digest if you write it in this form where these are your coefficients for the x squared, x, and constant term. But you can use the quadratic formula and you can solve for this and you'll get two values for x. And the only one that has significant physical significance is the one that's positive, and that's 1.1 times 10 to the minus 4. And this is really important because we know that our final partial pressure or our final mole fraction of NO is going to be 2x. So that's 2.2 times 10 to the minus 4. And we said that the mole fraction is the same as the partial pressure, which is what the question is asking us. So this is our final answer, which is answer choice C. Let's move on to the last question, question 36. Sodium sulfate is slowly added to 1 liter of solution that is 0.1 molar in both Pb2+ and Sr2+. How much Sodium sulfate must be added to induce precipitation of strontium sulfate. The Ksp of lead sulfate is 1.8 times 10 to the negative 8th, and the Ksp of strontium sulfate is that. There's quite a bit going on here, so it might be helpful to draw a diagram. You know that you have a 1 liter solution, and in the solution you have Pb2 plus lead ions, and you have Sr2 plus strontium ions. And the initial concentrations of these are both 0.1 molar. We're trying to induce the precipitation of strontium sulfate by adding to this Na2SO4. So the goal is that this sodium sulfate is going to dissociate into Na plus ions and SO4 2 minus ions. And these SO4 2 minus ions are going to see the strontium and react to precipitate out the strontium sulfate. The problem is that we have two competing processes. So the sulfate can go to the lead and create the lead sulfate, or it could go to the strontium and create strontium sulfate, which is what we want. So we have to look at which one is going to be precipitated first. If you recall what Ksp is defined by, it's going to be for lead sulfate, for example, is going to be the concentration of the lead times the concentration of the sulfate. And the same goes for strontium sulfate. The Ksp is going to be Sr2 plus times the concentration of the sulfate. Now we know we're given the final values of Ksp for both of them, and we know the concentration of the lead and the strontium ions. We know that they're 0.1, which allows us to solve for the concentration of sulfate required to induce precipitation of both lead and strontium. For strontium, the concentration of SO4 required is going to be the Ksp of the strontium sulfate divided by the concentration of strontium. So this is going to be 3.5 times 10 to the minus 7th divided by 0.1. This is 3.5 times 10 to the minus 6th. So we're going to need 3.5 times 10 to the minus 6th concentration of sulfate to induce precipitation of the strontium sulfate. We also have to look at the lead one though. So for lead, the equation is practically the same, except now you're looking at the Ksp of the lead sulfate reaction, and it's divided by the concentration of the lead this time. So this is going to be 1.8 times 10 to the minus 8 divided by 0.1, which is 1.8 times 10 to the minus 7th. Now here's where the problem lies. This value is a lot smaller. This value is a lot smaller than that value, which means that it's going to take a lot less of sulfate added in order to start precipitating the lead. In fact, you need a lot less. It's a whole order of magnitude. So what's going to happen is that the lead is going to start precipitating out until it's fully precipitated out, the solution is saturated, and the sulfate can start going towards the strontium. So the timeline goes kind of like this. The sulfate is added, the sodium sulfate is added, and when it reaches this concentration, the lead sulfate is going to start precipitating out, and it's going to precipitate out until all of it is precipitated. So since we have 0.1 molar in a 1 liter solution, we're going to need 0.1 moles of SO4 2 minus to completely precipitate out the lead, and then you can start precipitating out the strontium, and you're going to need 3.5 times 10 to the minus 6th moles to do that. And since these are such different orders of magnitude, we can say this is about 0.1 moles. And the answer choice closest to that is D. And that was the equilibrium section of the 2024 USNCO local exam. I hope this was helpful. I hope you were able to learn something. Please consider leaving a like and subscribing, and I'll see y'all later. Peace.